Okay, hello everyone. This is the fourth lecture of our course on EP1027, Maxwell equations and electromagnetic waves. So the agenda for today's lecture is the following. First, I will begin with a brief recap of what we did in lecture 3. In particular, I'll focus on the geometrical interpretation of gradient, divergence, and curl. And we'll learn about we'll review a little bit about the Gauss and Stokes theorem. And we will also revisit the continuity equation, which was covered at the fag end of the class, so hopefully we will cover it a bit more slowly this time. And then I'm going to talk about curvilinear coordinate systems, which are very important when studying electrodynamics because a large class of problems are more conveniently solved if they're set up in coordinate systems that are different from the Cartesian rectangular coordinate system which you're used to. In particular, I'll focus on the spherical and cylindrical polar coordinate system, and we will learn about the line element, the area element, and the volume element for each such coordinates, curvilinear coordinates. In particular, we will focus on orthogonal coordinate systems in which the coordinate axes, which are now curvilinear, which means they're curved lines, and they will, despite being curved lines, they will meet each other at 90 degrees. And then we will learn the expressions for gradient, divergence, and curl, and of course Laplacian in these coordinate systems. These are the four things we need when we formulate electrodynamics or we are solving problems of electrodynamics in curvilinear coordinates. And then I will give a general case when we will discuss general orthogonal curvilinear coordinate system apart from spherical and cylindrical. This will put you in good stead when you are solving at problems which do not have spherical or cylindrical symmetry, but some other form of symmetry, for example, parabolic or elliptical. And then finally, and perhaps the most important thing we will cover today in the class, is the Laplacian of 1 over mod x. X is the position vector. So this will lead to Laplacian will lead to the definition, or we will come across a new quantity which is known as Dirac's Delta function. It is denoted by this. Actually, there should be a 3 here, cube here, because delta cube of x, because this delta of vector x means this is the product of 3 delta functions in Cartesian coordinates. Okay, so the references for this class, Griffith's chapter 1 contains everything what I've been talking about. People who are looking for a bit more detail can look up the Schwarm's outline of vector analysis by Spiegel, chapter 7 in particular. And of course, Emil Bohr's mathematical methods for physical sciences. Chapter 10 contains the discussion on curvilinear coordinates. Okay, so let's start by reviewing the geometrical meaning of gradient, divergence, and curl. Gradient, remember the way I gave the geometrical interpretation of the gradient is that we consider an infinitesimal cube around this position x. Around location x, we had an infinitesimal cube, and this integral evaluated on the faces of the cube divided by the volume of the cube in the limit when the volume goes to 0, that is each of these lengths dimensions of not a cube but a cuboid. When the dimensions of the cuboid individually go to 0, in that limit this surface integral divided by the volume gives you the divergence, the gradient of the scalar. Okay. N hat here is the unit outward normal on the surface. It doesn't have to be a cuboid. I gave an example of a cuboid, but you can take any surface which is any infinitesimal volume which encloses the point x, and then S is of course an element of the area which is the surface enclosing that volume. Similarly, divergence, again a similar situation. So here we have vector field A and a location x, and we're considering an infinitesimal volume which includes the point x. Then the flux of the vector field on the surface of this volume, this flux divided by the volume in the limit that the volume approaches 0, gives you the divergence of A at the point x. Okay, so divergence is the flux over an infinitesimal closed surface per unit volume enclosed by the surface. And similarly, if we consider the curl of a vector field, curl of a vector field, the way we had defined, is that you have some loop, in this case a rectangular loop in the YZ plane with dimensions delta y and delta z, and the circulation of the vector field along this rectangular loop, which is given by this closed line integral. By definition, by the way, I haven't defined what line integral is, but line integral, this dot product, a dot the element of the loop, the tangent of the loop, this dot product is called, an integral of that is called the line integral of the vector field A. So line integral along this loop, whenever you have a closed line integral, we call that a circulation. Okay, so line integral in a closed circuit is called a circulation. So circulation of the vector field A along this rectangular loop divided by the loop area gives you the component of curl which is normal to the loop. Okay, and most of you know in high school you've come across the fact that area is or two-dimensional area is actually a vector quantity given by the cross product of the two edges or two vectors which define the edges. So this has a normal, so this gives you the component of the curl which is normal to the YZ plane, which is the x in this case. Okay, so curl in one line, curl is the anti-clockwise circulation. So anti-clockwise circulation of in an infinitesimal loop per unit normal area bounded by the loop. Okay, and then as I said that these two theorems in particular, you can transfer the delta V here and the delta SYZ here and integrate over a finite surface to obtain something which is known as the divergence theorem and the Stokes curl theorem. So divergence theorem tells you that the flux of a vector field over a closed surface is equal to the volume integral of the divergence. So I'm not sure how many of you are familiar with this notation d3 of x. d3 of x vector. d3 of x vector means this is dx, dy, dz. Okay, so this is something which I have been using in my slides, perhaps without explaining it. Perhaps it merits an explanation. So this term is symbol if you have not encountered before, then right now I'm telling you that this is d3 of x vector, and this is supposed to mean the volume element dx, dy, dz. Okay, so it tells you that the flux of a vector field on a closed surface is equal to the divergence, volume integral of divergence over the volume which is enclosed by this closed surface. And Stokes' theorem tells you that the circulation of a vector field along any arbitrary closed loop is equal to the flux of curl A on the surface which is bounded by the loop. So this ds, you can think of many closed surfaces, many open surfaces bounding the same loop. For example, if I take the loop to be a circle, it could be that loop can be that loop is bounding many surfaces. So this is not unique. The left hand side, unlike the case Gauss divergence theorem, the Stokes theorem, the left hand side, although it is right hand side, although it is unique, the left hand side, the surface S is not unique because there are multiple open surfaces which bound the same closed loop. Okay, so you should go from here to here. In particular, you can take the surface to be, if the closed loop is a planar loop, you can take the surface to be the planar surface as well. But you don't have to. You can take some other surface which doesn't lie in the same plane as the loop C. For example, if you take a disk, right? You can take a disk. The disk is bounded by the boundary of a disk, which is a circle. But then I can also imagine a hemisphere, which is to which the boundary of the disk is an equator. Okay, so we have two surfaces: the disk itself, which is a surface, and the hemisphere. Both of them are bounded by the same loop, which is the equatorial circle. Okay, so Stokes' theorem applies equally well to both cases. The right hand side is unique, but the left hand side is, although the surface is not unique, the answer is going to be unique in all. they're going to be the same for all the different surfaces which of which the boundary of which is we have this closed loop C. So I wrote this in a very schematic manner. I didn't write what these area element and volume elements are, and the reason is that I think these are conveniently worked out not in Cartesian coordinates but in curvilinear coordinates. So we will have to know what these are in curvilinear coordinates. Okay, the line element, the surface unit outward normal to a given surface, and this is the surface element. Okay, the final thing which we want to review is the continuity equation. This is a very important consequence of Gauss theorem, and it has some physical importance. As I said, all conservation laws are continuity equations that are written mathematically or expressed mathematically in the form of a continuity equation. So the beginning of that was to start some kind of a density of a conserved quantity like electric charge or mass. So rho is the mass density or electric charge density, and we have a given volume V. The total amount of charge contained in that volume is of course given by the volume integral of the density. And let's say these charges or these particles are in motion, so that this density is changing. In particular, this volume V is bounded by a surface, and any charge which is decreasing or increasing must pass through the surface which is bounding the volume V. Any change in the amount of charge contained in V must happen through exit from the boundary or entry from the boundary of V, and that is computed by looking at the flux of the material, flux of the charges or masses through the surface S, and that is given by this quantity. So it's the flux of the material from the surface. J is something which is known as the current density. It could be charge current density, it could be mass current density in the case of if rho is the charge density or the mass density respectively. So this is the amount of this is the way we define J is it's the amount of matter or amount of charge crossing a given area per unit normal area per unit time. Okay, so it's like you consider a small rectangular loop, then the amount of matter which is exiting normal to the loop, normal to that surface per unit time is what J is. Okay, so this is the amount of matter per unit time. This is the amount of flux which is outward flux, because N is the outward normal. So this gives you the outward flux. So this is the amount of charge which is escaping per unit time, or amount of mass which is escaping per unit time. But then this escaping of mass should lead to reduction of the charge or mass inside, and that is the rate of change of that is of course ddt of the rate of change of the total charge. And because there are no sources of sinks from which charges can disappear or mass can disappear, this is an alternative statement, alternative way of saying that the mass and charge are always conserved. If they are not conserved, there will be sources of sinks from which mass will or charge will appear or disappear into. So then these two must be exactly the same, and equating these two we get this flux per unit time is equal to reduction of charge per unit time. And then we used Gauss divergence theorem to convert this closed surface integral into the volume integral of the divergence of this quantity. And then this guy, what we did is we pulled the time derivative inside, and whenever we do that, I explained in the last class, when you have total derivative, when you push it inside a volume integral, you have to convert the total derivative into a partial derivative, because you don't want this to affect any of the spatial coordinates. So you have to, rho can be a function of x and t. So when we pull it inside, you can show that this must be the partial derivative. Total derivative when pulled inside an integral sign must give you the partial derivative. Once you do that, so we have the left hand side equal to this volume integral of the divergence of J, and the right hand side is equal to the volume integral of minus del rho del t. So we have these two, and then these two volume integrals can be combined into a single volume integral when we bring this to the left hand side, and this is 0. If this is this must be true for all volumes including infinitesimal volumes. So for infinitesimal volume, of course, this means this is non-zero, so this guy has to be 0. So this is a statement of the conservation of charge or conservation of mass, depending on what rho and j are, whether it's mass density or charge density, and this is mass current or charge current density. So del rho del t plus divergence of j equal to 0. As I said, this is the first physical formula in the course which we have learned so far. The rest of it is mostly mathematical preliminary and mathematical introduction. But this is a statement of physics continuity equation, and you should commit, it is something we should commit to memory. Okay, I hope things are clear. So this is where I'll end the recap. This is where we ended in the last class, and I'll move forward with our agenda today, which is to learn about spherical curvilinear coordinate system, beginning with cylindrical polar coordinates. So I guess some of you are already familiar with these coordinate systems from some other courses in mathematics department, or EP students are probably familiar with this from the physics courses as well. The cylindrical coordinate system is one in which a point in Euclidean three-dimensional space R3 is specified by not x, y, z coordinates, the Cartesian axis coordinate, but instead three different coordinates. So one of them is a distance, the other is an angle, and the other is of course a coordinate. So there's a difference between distance and coordinate. Distance can only be a positive definite quantity, positive semi-definite quantity, while a coordinate can take plus or negative values, and phi is of course an angle. So this is how you define them. So you have the usual Cartesian set of axes, and this is the point P, which had in the Cartesian coordinate systems its coordinates to be x, y, and z. Instead, in the cylindrical polar coordinates, it is given by rho, phi, and z. Rho is this distance. You drop a perpendicular of this from the xy plane to the xy plane, and the point where it hits the xy plane, you draw a you join it from the origin with a line segment, and the distance from the origin to the point where you have dropped a perpendicular on the xy plane, that distance is known as the radial distance rho, or radius rho. Okay, this quantity rho, and then the angle made by that this line which joins the origin to the point where you had dropped a perpendicular on the xy plane, the angle which it makes with the x-axis is called the angle phi. So, it is known as the azimuth. Most of you are familiar with this term, azimuthal quantum number in chemistry, or in high school chemistry, or even some physics courses. So this gives you the azimuth, or the azimuthal angle. And then z is the usual Cartesian z coordinate, which gives you how high from the xy plane this point P is located. Okay, so these three, the radial distance, the azimuth, and then z is called the axial coordinate, or axial, because z, it's a cylindrical coordinate system. A cylinder has an axis, and then a cylinder also has a radius. So this rho is the cylindrical radius. You can think of imagine a cylinder, and z is of course, so this is the radial distance, the azimuthal angle, and the axial coordinate. These constitute the cylindrical polar coordinates. Now, of course, using plane trigonometry, you can relate phi, rho, and z to their Cartesian coordinates and vice versa. So this is what I have, the map. So x, most of you can work this out by elementary trigonometry, how x, y, z are related to the, how, if you know rho, phi, and z, this first line gives you how you can recover your Cartesian coordinates, and the second line is the inverse map. Given x, y, z, what are the values of rho, phi, and z? So first thing you will note is that phi is non-unique, because you have to take a tan inverse, which is a multi-valued function. So phi here is non-unique, and also there is a problem defining phi for points which lie on the axis, right? So phi is defined to be this angle from this radial distance, this radial line makes with the x-axis. But what if this radial line is not there because the point lies on the axis? In that case, phi is indeterminate for that point. and it's not a so this coordinate system is only a good coordinate system if you exclude the z-axis. Anywhere away from the z-axis, given a point xyz, which doesn't lie on the x-axis, then you have a nice map between them. But on the x-axis, phi is indeterminate, and it ceases to be a good coordinate system. Okay, so another important thing which we need are the unit vectors. So in the xyz coordinate system, most of you are very well aware that the unit vector is along the three coordinate axes. Oh, so maybe I should say a word about the coordinate axis. So remember how recall how you define x-axis for in the Cartesian coordinate system. X-axis is given by given by the condition that z and y are fixed. Okay, if you fix z and y, the lines of constant z and constant y are the x direction, so that is an axis, right? So here x and y, all along this, x and y are constant. In particular, they are 0. Similarly, the y-axis is defined by the condition x equal to 0 and z equal to 0. Similarly, the rho axis is defined when phi and z are 0. Phi and z are fixed. So if you fix z and phi, so let's see. So constant z lines are what? Constant z lines are of course the planes. For example, if I fix if I make z equal to 0, that gives you the xy plane. Similarly, z equal to non-vanishing will give you some plane which is parallel to the xy plane located somewhere here. And then constant phi is a half plane, right? Phi is constant here, so this plane um, for which phi is constant is the constant phi plane. And then this is a half plane because it can only go up to it can start its boundary is the z-axis, right? And then it can continue in this direction indefinitely. Constant that is the constant phi surface, and the meeting of these two, intersection of constant phi surface and the constant z surface, one is a half plane and one is the full plane, gives you the rho axis. Right, so the rho axis will be along this arrow. If you think a little bit, you'll find out that the rho axis is given in the direction of increasing rho, and phi and z are not changing. For this small arrow here, little arrow, gives you the rho axis. Similarly, you can find out the phi axis will be given by this small arrow, which is orthogonal to the rho axis, and z unit vector is, of course, the vertical unit vector, which I have not drawn because it will make the figure a bit more complicated, cumbersome. So I've only drawn the new ones, which the rho hat and the phi hat, which are the unit vectors. Now these unit vectors, again, you can use simple trigonometry to write down in terms of the usual Cartesian unit vectors. So you can show that rho hat equal to is this. Again, just apply plain trigonometry. So rho, it is very clear, rho is the unit vector along this direction, but this direction has x coordinate equal to x and y coordinate equal to y and z coordinate equal to 0. So any unit vector along that along the position vector x comma y comma 0 is given by this. Similarly, for phi, you can show this is equal to minus y x hat plus x y hat divided by 0, because for this vector, if you bring this to the origin, it will point out to the orthogonal direction to this. So x and y will get interchange, and y will pick up a minus sign because the x component is negative because this points in the negative x-axis, along the negative x-axis, something like this. And of course z vector remains unchanged because z coordinate is common to both cylindrical and Cartesian coordinate systems. The inverse map, you can also find out the inverse map if you know these, using x and using the inverse, using this map. Using this map, you can invert this map. Using the map of the coordinates, you can invert the map for the unit vectors, and you'll have these Cartesian coordinate vectors, Cartesian unit vectors in terms of the cylindrical polar coordinate basis vectors, phi hat, rho hat, and z hat. So I forgot to mention why it is a curvilinear coordinate, because the rho axis, which is constant phi and z, is a circle, right? The circle is not a straight line, of course. So the rho axis is a circle. So in this case, the axis is the curve. I'm sorry, not rho axis. I'm talking about the phi axis. Phi axis is a constant rho and constant z line. So constant rho means radius must remain the constant, which means it must be a circle, right? Constant rho must be a constant radius circle. So phi axis is a circle. So that's why it's a curvilinear coordinate, because the phi axis is a curve. In particular, it's a circle. So these were for the basis vectors. Now once we know the map between the basis vectors, we can write down a general component of a general vector and convert it into a basis. So x, all we do is we start with the Cartesian coordinate description of some vector field. So A is a vector field. In fact, it could be a vector. It doesn't have to be a vector field. But of course, we are going to talk about vector fields in this course, so it's better to think of A as a vector field. But nonetheless, this applies in general for all vectors, whether it's a field vector or a single vector. So you have vector with these components in Cartesian, A1, A2, A3. And what you do is that you substitute, instead of x hat, this Cartesian Cartesian x basis vector in terms of the polar vectors, and then you, whatever you have, do that for the y, do that for the z, and assemble terms which have rho hat, and that gives you the rho component of the A vector. So here I have written down for your convenience, but you can check. Once you substitute x equal to this and y hat equal to this and z hat equal to this, and then assemble everything which contains rho together, you will get that the rhoth component of a vector is given by ax cos phi plus a2 ay sin phi, and then something like this, and then something like that. The third component is of course the zth component. There is no change in that. In particular, you can do this for the line element. Remember, what is the line element? Line element is the infinitesimal position vector change, which is given by, it's the distance between 2 points x. It's a vector connecting the points x, 2 points defined by the position vector x and x plus dx. So that is called the line element. So the line element is given by this. Actually, I'm sorry, this is not. Yeah, no, that's fine. Line element, which is dx x hat, dy y hat, dz d hat. Of course, you can, again, you do the same thing. X, you know what is it in x, y, z. You can find out what dx is in terms of d rho and d phi, dy in terms of d rho and d phi, and dz in terms of dz. And then, of course, these unit vectors also, you know how to convert it into, map it into polar basis vectors. And if you do all that, what you find is that in polar coordinate, the same line element, in this case, joining 2 points which are given by by position vectors x and x plus dx, or in cylindrical coordinates, rho phi z and rho plus d rho, phi plus d phi, and z plus dz is given by this expression. Okay, so it's d rho hat, rho d phi hat plus dz z hat. Okay, so this is intuitively clear why it is. A little bit of increase of radial distance will be in the radial direction. A little change in the phi coordinate will be accompanied by the distance radius times small change in angle. and then vertical distance or change in the position due to vertical coordinate will be dz times c. This is pretty clear. And then you can ask about what about the volume element. Volume element in this coordinate is defined by the, as you know, the scalar product of three vectors. Volume which is bounded by these three sides, one side, the other side, third side. These three vectors are bounding the side of a cuboid, and the volume of cuboid bounded by three vectors a, b, and c, as you know, is a dot b cross c. So I've used that formula which you have learned in high school and shown that the volume element is given by this. Mind you that if you write down, this is the same cube as formed by these vectors. If you write down dx dy dz and then use the Jacobian rule to convert from dx dy dz to d rho d phi dz, you will get the same. This you can do as an exercise. This I've directly computed the volume element, but you can do indirectly as well. You can start with the Cartesian coordinates, and then in Cartesian coordinates the volume element is dx dy dz, and then use the Jacobian rule for converting the volume element from one set of coordinate to the other set of coordinates using the Jacobian determinant, and you should get the same result. Okay, I hope people are familiar with the notion of a Jacobian when you transform in multivariable calculus, when you're making a multivariable integral calculus, when you're doing a change of integration variables, multiple integration variables at the same time. Then you need a Jacobian for the measure transformation of the measure dx dy dz. Okay, once that is out of the way, once that we understand how line elements and volume elements work out, we might want to look at the gradient operator, because in electrodynamics we will need that. So gradient operator, how does it look in cylindrical polar coordinates? The way to figure this out is to start from the defining equation for the gradient, which tells you that if you consider a scalar field, and if you're interested in computing the difference in the value of the scalar field at location x and at location x plus dx to infinitesimally close points, and you are asking the question, what is the difference between the scalar fields located at those two infinitesimally close points, and that is given by if you apply Taylor expansion formula, as I said, that dx dot del times phi. This is how we arrived at this. Now we did this in a sort of Cartesian way, but let's say I don't want this equation is true regardless of whether I use Cartesian coordinates or not. Then what happens is, let's say I'm using cylindrical polar coordinates. So cylindrical coordinates, again I can do the this compute this quantity not in which is defined by this difference, not in Cartesian coordinate but in cylindrical polar coordinates, and I know from multivariable calculus a small change will be given by this partial formula. This is a small change in rho, phi, and dz, and how a function which depends on rho, phi, and z responds to what is the change when you make infinitesimal changes in the variables rho, phi, and z, and that is given by this formula. So the left hand side of this equation 2, defining equation 2, is this, and the right hand side, so dx dot del, dx we know in what it is in the line element is in cylindrical coordinates. So we know this and we know the left hand side. From that we can compute what this del operator is, and it turns out the del operator should look something like this: rho hat times del del rho plus phi hat times 1 over rho del del phi and z hat times del z. So if you it's a unit vector, so the unit vector is a dimensionless. If you look carefully, each term has dimensions 1 over length. So del del rho is 1 over length, 1 over rho times the angle, that is also 1 over length, and this is also 1 over length. Okay, so this gives you a cool way to check whether this is correct or not. If you have expressions, each of them should be 1 over length expression. So especially because to keep in mind that the unit vectors are dimensionless objects, because by definition they have magnitude unity. Um, Similarly, you can use the geometrical interpretation. You can use the, I'm sorry, let me just go back. Yeah, this geometrical definition of divergence, you can use this to figure out what is the expression for. You can find this left hand side. If you find this, compute this left hand side, automatically it gives you the expression for divergence of A. And instead of using, for example, a Cartesian volume element, you can take a curvilinear volume element, and which would be a cuboid with curved faces. And for that, if you compute the flux through the outer surfaces, through the surfaces, the bounding surfaces of the curved or curvilinear cuboid divided by the volume of the cuboid, that gives you the expression for the divergence of a vector in curvilinear coordinate system, in particular in cylindrical polar coordinate system. And as I've said, the derivations are provided in supplementary notes, which I will put up. And there you can see how exactly you arrive at this. However, in general, you don't need to know how to do the derivation, but the important thing to know is the expression. Again, this should be a 1 over length dimension, because gradient is 1 over length. This guy is pretty clear, 1 over length, 1 over length, and this is 1 over length square, but then we have multiplied by rho, so it's also 1 over length. Okay. Similarly, from the geometric definition of curve, in which you consider, for example, a loop in the phi z plane, on the phi z plane, and that will give you the rho component of the curl of A. You use this definition, find out the circulation of the vector field on the phi z plane, divided by the area of the loop in the phi z plane. That will give you the rho component of the curl, and you will arrive at this expression. If you do that, just following plain rules of multivariable calculus. So these don't look as as intuitive, because they're a bit nasty. But except maybe for this, which is very simple. It's just like your Cartesian formula. This formula also, with some effort, I can find a way to easily memorize, but this is a bit complicated, right? 1 over rho del rho fi minus, so it's not easy to remember. In the end of this section, I will tell you how to have general formula for each general formula for in general coordinate system. Perhaps you can memorize those and then apply for the special cases. Laplace operator is also a bit complicated. You have to act twice on this divergence. Sorry, not this. Laplace operator acts on a scalar, or a component of a scalar, as component of a vector. So you have to apply a second time on this, and if you do that, you will arrive at this expression. Okay. Again, I'll do the derivations in supplementary notes, but the reason I put them in the supplementary notes is because you don't need to know the derivation, but it will suffice if you just know the result. Another important coordinate system which we study is something which is known as the spherical polar coordinate system, in which a point in this three-dimensional Euclidean plane is labeled by r, theta, and phi instead of rho, phi, and z. So r, theta, phi, as indicated, you can see in the diagram. You can also look it up on the book. P is the point for which we are computing this. So the distance from the origin is the radius, r, and this angle theta from the z-axis is sometimes known as the co-latitude, because it is the complementary angle to the latitude. So latitude would be this angle made with the xy plane, and then this is 90 minus that latitude. That's why it's called the co-latitude. And phi is the azimuth, or the longitude. Okay, phi is the longitude. Again, its in relation to Cartesian coordinates can be easily found out from elementary trigonometry. So this is the map, and this is the inverse map. Again, as I said, the inverse map is not always unique. In particular, the um, phi coordinate is not defined on the z-axis, as I've said before. Unit vectors, I haven't drawn those unit vectors, but if you can imagine that the r hat is the unit vector pointing along the radial direction, so it will be in this direction, and that is easy to compute because you know the sides of the triangle. Which is given by this formula, and then the theta direction, which is a bit more complicated, but nonetheless it can be done. So theta is going clockwise like this, so theta will be, you can imagine a vector which is pointing out in this downward direction slightly, so it's 90 degrees to this theta. It's not 90 degrees, 90 degrees to this r, and again from elementary trigonometry you can figure out what these are. And then you can invert this map to write down x in terms of r theta and phi. Okay, I have not written the y because it is a bit longish formula, but you can do it yourself. It just requires elementary high school trigonometry. And then once you know, you can convert a regular vector into its counterpart in spherical polar coordinates, not just the position vector. This is the general vector. So once you plug in this, you get the components. The line element also can be converted easily. All you have to do is to write down d of x in terms of d of r, d theta, and d phi, and x hat in terms of r hat, theta hat, and phi hat, and you'll arrive at the expression for the line element, which is given by this. The volume element will be given by the vector scalar triple product of these three. It's a cuboid with these three as the edges of the cube. So one thing I didn't mention, I think I forgot to mention for the cylindrical coordinate system, which is true for the spherical coordinate system as well, is that if you take the dot product of these two, it will give you 0. If you take the dot product of theta and phi hat, theta hat and phi hat, that will give you 0. So these are orthonormal triads, just like your Cartesian coordinate system. R hat, theta hat, and phi hat constitute a right-handed orthonormal triad. Expression for the gradient can be simply obtained. As I said, just follow the same rule as before. You compute this. You start from the defining equation d phi equal to this, and then d phi you can write using rules of multivariable calculus. Dx also you can write using the definition of the line element. From that, then work out what the expression for del operator is, and from the geometrical interpretation of divergence and of curl, you can extract the expression for the divergence and curl as well. And as I said, the curl expression is a bit long and it is not so intuitive, so I didn't put it on the slide. It's not that you'll get something by looking at the expression from the slide. You don't really get anything. It's just a complicated looking expression, that's all. So that's why I didn't bother about putting it on the slide. And then this is the Laplace operator. Again, it's not something you can easily find a pattern worth remembering. So I would, you can look for it, but it is not easy to remember where the theta, sine theta will appear and where and when. So, these are forming a pattern. The last two examples, we took the cylindrical polar coordinates and the spherical polar coordinates. They can be thought of as a part of a general set of coordinate system which is known as orthogonal curvilinear coordinates, in which the coordinate axes are curved and also the unit vectors will form an orthonormal triad. Okay, although despite the fact that the coordinate axes are curved, the unit vectors are going to be intersecting at 90 degrees. Okay, so this is a general set of coordinates q1, q2, q3. Could be r theta phi, could be rho phi z. In general case. The unit vectors is you obtained as a vector along one of the axes, right? So the unit vector along the q1 axis would be when you hold q2 and q3 constant. So you have the position vector, take its partial derivative with respect to q1. This gives you a small vector in the direction of q1. And then, of course, this is proportionality. You have to put back the proportionality factor so that this is the norm of this is, this is not a unit vector. This is a unit vector, so the difference is given by the magnitude, which is h1, sometimes which is known as the scale factor. And the line element, which is written in this way, so this just using all we are using is rules of multivariable calculus, differential calculus. So we have a vector, small change is because of small change in these coordinates. So in general, you can write using the Einstein summation convention that this is del x del qi times dqi, and del x del qy, as I said, is the unit vector along the ith direction times the scale factor. So this is the general kind of expression for a line element along a general orthogonal curvilinear coordinate. The length element is given by magnitude of the line element, which is dx dot dx, and then because they are orthogonal, this will be hi square dqi square. Sum over all I is implied because I is a repeated index. The volume element will be given by the scalar triple product of these vectors. So 1, 2, and 3, and you can see this is h1, h2, h3, dq1, dq2, dq3, right? So it would be a good exercise to work out these what h1, hi's are for, let's say the spherical polar coordinate system or the cylindrical polar coordinate system, and verify that indeed this gives you the usual length element and the volume element. Again, gradient you can work out, as I said, using the same trick. This is using rules of partial differentiation in multivariable calculus, and not partial differential, total differential. This is total differential in terms of sum of partial differentials. And then dx you already know, the line element we just worked out. From that, equating these two, you can figure out what the del is. And del is given by this 1 over scale factor times del phi del qi, the partial derivative along the ith direction, ei. Because I is repeated, this is a summed over all I. However, this formula is a bit weird because the same index has been repeated 3 times, right? So ei had, qi and hi. The index I appears 3 times. This is one of the few cases where the Einstein summation is a bit ambiguous, as far as I can tell. That despite the fact you have 3 indices, this expression is still consistent. This doesn't lead to any inconsistencies. But you have 3 indices of the same kind. The divergence of A, again you use the general way of determining this using the geometric meaning of divergence. You take an infinitesimal volume and then compute the flux and divide by the magnitude of the volume. That gives you the divergence, and the limit the volume approaches 0. So that is given by this not so pleasant looking expression. However, there is a pattern to this. So 1 over h1, when you divide by the volume, you get 1 over h1, h2, h3, because these are the edges of the cuboid. And then there is a pattern 2, 3, 1, 3, 1, 2, and 1, 2, 3. Perhaps this is easier to remember when the general. So the general case is easier to remember than the special cases, which is spherical and cylindrical polar coordinates. And the curl, for example, the third component, E3 is the third component, not to confuse with the z-axis, because here we are not considering z-axis but the third coordinate Q3 in general. So that is given by this formula. Again, this is if you remember the geometric interpretation of curl, it has some flux or not flux circulation divided by the area element. So if you in the 3 direction, the area element is aligned, it lies on the loop lies on the 1, 2 plane. So that's why the area on the 1, 2 plane will be proportional to 1 over h1, h2. Not 1 over, it's just proportional to h1, h2, and you divide by the area, that's why it's in the denominator. And then from dimensional consistency, you can work out what this should be. So it should have 1 over length, that means one factor of length has to be cancelled. Okay, and the Laplace operator looks something like this. Again, not something very nice, it's pretty nasty. And there is still a pattern, I would say. It's easier to remember than the special cases, which is the cylindrical and spherical polar coordinate. Okay, so this was sort of a very quick and lightning tour of the orthogonal coordinate systems. I'm sure you'll have a lot of open questions. Please look up the references or the readings which I was suggested at the beginning of the lecture, and you'll be good to go. Final thing today which I want to cover in the lecture today is something which is known as the Dirac Delta function. I've written function within quotes, which just means it is not the function in the usual sense. So what is the exact definition in part A I have called, because this is not the best way to define. So the Dirac Delta function in one dimension, that is one where single variable is an object depending on the single variable x in the following way. It is 0 whenever x is non-zero, and at x equal to 0 exactly it is infinity. So the graph looks like a single spike at the origin. So this is how it looks like. Everywhere it is 0 except at x equal to 0 when it blows up, right? So anything which blows up is kind of undefined. We don't know how to define it. The behavior at that point is singular. So actually this is why it's not a function. It's something which is known as a distribution, and we can make it well behave within an integral. Whenever we can do that, that categorizes a different kind of object in mathematics, which is known as a generalized function or a distribution. So this is the exact definition part B. Now it is let's say this delta function has been defined within an integral minus a to plus b. So some minus a to plus b somewhere here. Now this tells you that this is equal to 1 if a and b are positive. So that is this interval integration range, if it includes the location of the spike, then it gives you 0. If this integral is outside if the range of integration doesn't contain the spikes, then we are integrating just 0 over everything. Oh, sorry, I confused myself. So this is just the integral of the delta function, and here we have the integral of delta function with some other function, which is not a distribution. This is a smooth, nice function. And if you have an integration range which encloses the location of the spike, then the answer is equal to, you just put f0, the location of the delta function. Okay, so that is what is the best way to work with the delta function. These two definitions are going to be useful. So this is a special case when fx is equal to 1. But in general, if you have integral of a delta function and a normal function fx over a range which includes the spike, then that should give you f at the location of the spike. Okay, if the spike is outside the range of integration, then the integral identically vanishes. So I've written a and b plus, they're both positive, so that means it doesn't include the origin 0. Or if a and b are both, the upper and lower limit are both negative, so again that doesn't include the origin. So these will give you 0 values, and similar for the function fx, for arbitrary normal function fx. Okay, so this is how you define the delta function. So one way, as Griffith tells you, if you read Griffith, it will tell you, is one way to think about this delta function is to define it as a limit of a sequence of functions. For example, you can take take a rectangle of some length minus L by 2 to plus L by 2, where it is its height is L and width is. You can take a small rectangle symmetrically around the origin with height L, or this length L, and the width 1 over L. So the area of that rectangle is L times 1 over L, that is 1, right? So now you take the limit, gradual limit in which L goes to infinity and the width goes to 0, 1 over L then goes to 0. So the limit of a sequence of such rectangles will give you the delta function. Now the next thing is you can extend it to multivariable calculus. For example, this is the three-dimensional delta function. The three-dimensional delta function is delta time of position vector x. This is equal to delta of x, delta of y, and delta of z, product of three individual delta functions. As a result, let's say if I have some volume which encloses the origin at which the delta function spike is located. If the volume integral is around, for example, it could be a sphere of radius r around the origin. So this, you can break it up into three integrals. This means this is dx, dy, dz, and then this is delta of x, delta of y, delta of z, and then you can separate and do these three integrals separately. Each of them is equal to 1, so it gives you 1. Okay. So why do I need this delta function in electromagnetism? For this, you have to recall that in last couple of classes I've made this point that if you try to compute the Laplacian of 1 over r, which is 1 over absolute value, this magnitude of this position vector, that gives you 0. Usually it will give you 0, provided x is not equal to 0, not at the origin. Because if x is at the origin, these derivatives are not so well defined. Okay, so this is the expression which is suspect at the origin. Apart from the origin, outside the origin, it is always 0. So the idea is that the expression at the origin is given by, so it is something like it is some function which is in the vein of delta function, because it is 0 outside the origin and at the origin it is undefined. In fact, it blows up because it's 1 over x, and for the derivatives of 1 over x, so in fact it blows up at the origin and it is 0 outside the origin. So it is exactly like the delta function. In fact, it can be shown that it is proportional to the delta function. In fact, we show that the proportionality constant is 4 pi. So box square of minus 1 over x, or if you don't want the minus here, you can put the minus here. So box square of 1 over x would be equal to minus 4 pi times the three-dimensional delta function at the origin. And to prove this, we'll actually not rigorously prove this. Instead, I'll be happy with just verifying that this is indeed the case. So the fact that if you take single Laplacian as del dot del, if you act with the single del, you get this 1 over x will give you this. So let's check just this. Okay. So to prove that this is the case, I will use the Gauss divergence theorem. Gauss divergence theorem tells you that volume integral of divergence of A over some volume B, A is equal to the flux of that integral, flux integral of A over this S surface which bounds this volume B. For the case of interest, we will take x to be this vector, position vector divided by the cube of the magnitude of the position vector. So that is A, and then the volume of integration I will take to be the unit ball. Okay, unit ball is the region inside the unit sphere. So so S is the unit sphere. That means, okay. So let's compute both sides. And the left hand side, of course, we cannot compute right yet because we don't know what divergence of this quantity is. We have just said that it is equal to the delta function. We will check whether delta function can reproduce this right hand side or not. Okay, so let's work out the right hand side first. So right hand side, if you have a unit sphere, the radius vector is also the unit normal on the sphere. So that's what I've. The unit vector is then the radial vector divided by the magnitude of the position vector. Any point on the sphere, the line joining that point and the origin gives you the unit normal to that, or direction of the normal to that. So that is what I've used. So n is this, A is of course this we have taken. So if you do the dot product, you will find this is equal to 1 over r square, where r is magnitude of x. Line element of the sphere is very easy to write down, and most of you know it is r square sine theta d theta d phi. So this r square will cancel, 1 over r square will cancel with this r square. And then we'll have an integration of sine theta d phi. where theta goes from 0 to pi and phi goes from 0 to twice of pi. So if you integrate this, you get 4 pi. So this right hand side is equal to 4 pi. Now let's see if I take this definition on the left hand side, whether we reproduce that 4 pi or not. So here I plug in 4 pi delta. So this is 4 pi delta integral over the volume, but this volume includes the origin. So this will give you integral is 1, so it is also giving you 4 pi. Thus, both the left hand side and right hand side, if you assume the left hand side divergence of this is equal to 4 pi delta, indeed it gives you the 4 pi. So as I said, the Dirac Delta is not actually a function. It is best thought of as something which is known as a distribution, and this has been defined by Schwartz. In the mathematical, machinery of this has been invented by Schwartz, and it is only defined distribution as a distribution or a generalized function, and the idea is that these are only well defined inside the integral sign, and they should be always integrated against something which smooth functions known as test functions. I had an fx as an arbitrary function, but actually they was defined if they are smooth functions. Smooth means that all ordered derivative exists. Okay, C infinity means that it is continuous and it's differentiable to arbitrary degree, right? Nth ordered derivative is also finite and continuous. So then it is defined by this way, as I said, if this integral region, whenever I don't specify the limits of integration, that means it is over to maximal range, minus infinity to plus infinity. And this spike is located at x equal to a. So whenever you integrate this against this test function, what this delta function ends up doing is giving the value at pi equal to a. So if some of you might already see some resonance with the Kronecker delta function. Kronecker delta function, you had delta ij some bj, an integral over all j, giving you delta some ai. So this is, you can think of x is not a discrete label. It is not a label I runs from 1 to n in the discrete case, but this is a continuous label. So you can think of this delta Dirac delta function. This is the best way to think about it. It gives you a continuous version or continuum version of the Kronecker delta. Okay, that is what Dirac delta does. And you can also define derivatives of the Dirac delta function by using integration parts. So you use integration by parts, then you get a total derivative minus when the differentiation is transferred on the theta. This total derivative term will give you a term at plus minus infinity because it's the total ddx of integral of ddx. So that will give you the value of this at plus or minus infinity. At plus or minus infinity, theta is finite, but delta goes to 0. So this product goes to 0. That's why I've dropped it. So and then it shows that every expression you find in which you have a delta prime, all you should do is to put a minus sign and convert it into delta acting on theta prime. Okay. So any integral expression you find, and it can be applied over and over again. For example, if you have two derivatives, double prime, then it will be minus 1 square times delta x theta double prime of x. Each time the total derivative term will go to 0 because by assumption theta is this total derivative will get contribution from plus and minus infinity at both the upper and lower limits of integration. Delta is 0 while theta or whatever derivative of theta, they are all finite. So I will conclude by giving a very useful identity which we will use over and over in the course, which is when you don't have delta of x but delta of some other function of x. Okay, so x is the variable, but then we don't have delta of x directly, but we have delta of, let's say, x squared plus twice x plus a or something like that, some arbitrary function fx of. So what is it equal to? Well, it will turn out so let's say we have this integral, so we would like to convert it into delta of x. The way to do that is to find out first the roots of this function equal to 0. So these are the roots, f of ai, location of the roots, equal to 0. And then this delta function will have spikes only at those locations, because that is where the argument, remember the delta function has argument, blows up wherever has a spike, wherever the argument vanishes. So that's those are given by the roots of fx equal to 0. So there'll be a spike at each such root. So this will be a sum of spikes, and the normalization constant is 1 over the magnitude of first derivative at the spike, okay, and sum over thing. So this formula you can easily derive, as I say, by already motivated how to do this. You just check where the spikes are located, and then it's just a matter of finding out the norm of the normalization constant, or sorry, the proportionality constant. So this is the important formula we will use many times. This will be a quadratic function. So quadratic function has two roots. So it will be I will be sum over first root and the second root. Okay, this we will need. Okay, let's stop here. So this is a good point to stop. I think we have completely exhausted the mathematical preliminary part of the course. And now next lecture onwards, we will move on to electrodynamics proper. I will start with electrostatics. Okay. Okay, so see you in the next lecture. I'll stop here.